Good morning, everyone. Welcome to the second day. We'll start with talk.
Thank you, Madan. Yeah. Good morning, everybody. Good morning. So it's nice to meet you again. I will start the second day lecture. Today, we're going to look at the introduction to shock waves, and we'll start with that one. And then in the afternoon, we'll look at the application of shock waves in supersonic nozzles. So let's see what we have covered yesterday. We looked at the gas turbine propulsion systems. We looked at the turbojet, turbofan, turboprop, turboshaft engines, and the cycle diagrams. We briefly looked at the ramjet and scramjet as engine which has no rotary components, and then we looked into the combustion applications in this ramjet and scramjet engines using the Rayleigh theory, and then we tried to solve the problem. So that's what we looked at in the last yesterday's lectures. Today we're going to look at the numbers. It should be third. Look at the shocks. Introduction to shocks. We'll start with the normal shock ones. Now, first we will try to understand the mechanism of formation of shocks, but before that, let's look into the flows. Basically, this slide will be about discussing about the mechanism of how the signals are communicated when an object is moving. When an object is moving at subsonic speed, so you can see that before even so if you can just look at the red dot there, before even an object, the white object comes and meets the red dot, you could see that the signal communicates to that red dot well ahead in time that an object is traveling. So this is like the small pressure waves, an infinite small disturbance. So signals are communicated at the speed of sound. And the object, everything is known that something is coming, and the molecules arrange themselves and give way, and then the object moves. So this is how it is. In the olden days, it was thought that all particles will come and collide, and then it was moving. So that is not the case. Now, this is what happens under subsonic flow conditions. Under subsonic flow conditions, no shock will be formed at all. Okay. Now, when you look at supersonic flows, the object moves at a speed greater than the speed of sound. So you can see that all the signals are communicated, but still they are behind the object itself. So the object is ahead of the signals at which it is communicated at the speed of sound. Now, how is the object aware of that the molecules are aware of that the object is coming? And this brings us to the introduction of the shock waves. Okay, because in supersonic flows, unlike subsonic flows, the signals are communicated, but they are further behind. So the object goes ahead of this one. So just to not spend more time, just to give a very brief mechanism for the formation of shock waves. This is the plunger mode of description. Assume that you have a piston cylinder configuration, that a piston is moving continuously, but let's assume that it's moving in time steps. Yeah. So initially at time t equal to 1, the movement of the piston will impart that kinetic energy to the fluid particles here. Now that particle energy level will increase, and then the next impact in time t2 will magnify on the pressure and temperature of those particles which already had gained some energy here. And then in the next impact here, then you can see that the fluid particles which are already gained impact the 2 times is now being amplified. Now you see that this effect here, where the pressure waves tends to steepen in period of time. And when this pressure waves tend to steepen over a period of time, it tends to come to a situation where you look like the wave tends to topple. In that case, it is very unrealistic situation, which can never happen. Say, for example, at a different time instance, you have at a particular time there are 2 or 3 pressures, which is not possible. When it comes to that situation, the flow spontaneously jump, and that is what we call as the formation of the shock waves. In common terms, it is basically the pressure waves, they coalesce together to form a high pressure wave. That is what is the shock wave. Now, this is happening at a very short time period, and this is also happening at a very small spatial level. I think it's at the main free path of the molecule. So it's in the order of microns. So the shock waves itself, what's happening itself is a highly non-linear within the shock waves. But we are not really going to look into the shock waves. We are looking at what's going to happen because of the shock wave, how the properties are going to change before and after. That's what we'll be interested from the jet engine applications here. But realistically speaking, all of these events are happening at the molecular level. So which means that the molecules, they come and they collide with another molecule. When the collision is there, 2 molecules impinge, there is a force. The force will transform into pressure. This is happening millions of molecules at a high speed, and these coalesce to form this pressure waves. And that is what we call as the shock waves. So as I said, it is kind of a discontinuity. So for example, if you want to look at it, imagine you're going and looking at the waterfalls. In a waterfalls, you see that the water, so here the water is going to fall. So here you are here. So this is where it is. But when you are here, up here and looking down, this is what you'll see. You will just see that there is water coming from here. But then you don't know, but there is a strong discontinuity here. Then you see that suddenly the pressure is different from what it was here. So you can see that there's a strong discontinuity. This is how you can visualize it here. So it's a discontinuity in the fluid flow. It occurs in supersonic conditions here. So when you see that a shock wave occurs, all the properties spontaneously jumps. One of the things what you see here is that when the flow that is coming at supersonic, M1 greater than 1, immediately after the shock, the flow becomes subsonic. All the other properties, static pressure, static temperature, all increases, but the total pressure decreases. And the entropy, S1 entropy, will increase. All of the properties change. So after this spontaneous jump, you can see that there is you are able to have an increase in temperature, increase in pressure. We are going to take use of this advantage in aircraft applications under supersonic speeds. But also we're going to see how you could use the shock waves to decelerate the flow. A strong deceleration, okay, coming from whatever the high supersonic, immediately it becomes subsonic applications here. So if this shock wave is normal to the flow, then it's called the normal shock wave. The flows passing through the shock waves are highly irreversible, so we can't use any of the isentropic solutions. And we see that large change in properties occur across the shock, and the fluid particles decelerate across the shock. Static pressure, temperature, density, entropy, all of those static properties increases. But the total energy across the shock remains the same. It was during this period when the shock waves are being researched and developed. Prandtl was also working on the understanding how this flow changes. So when he was working, he proposed an hypothesis. He found that the velocity before shock was the Mach number supersonic, and then the velocity after becomes subsonic speeds. So he proposed this hypothesis that the product of the velocity before and after to be equal to the speed of sound. He didn't just refer it to the speed of sound, he referred it because the speed of sound is equal to square root of gamma RT. It is very much dependent on the local temperature, local speed of sound. So Prandtl proposed a critical speed of sound. So critical speed of sound is one which occurs at m is equal to 1. So accordingly, so Prandtl proposed, so V1 by C star into V2 by C star is equal to 1. Or in other words, so we know that Mach number is equal to V by C. So here it is M1 star and M2 star is equal to 1. So accordingly, Prandtl hypothesis, it says the Mach number after the shock will be subsonic. That is Prandtl's hypothesis. So this is the normal definition. Understood this one? Yes. This is the normal Mach number. Mach number is equal to V by C. But Prandtl proposition was that is divided by the characteristic speed, and that Mach number is m star is the characteristic Mach number. In many ways, they are equivalent to that of the local Mach number. For example, characteristic Mach number has a finite value. So the maximum value is, so for example, if m is equal to 0, then you can see that the characteristic Mach number is also 0. So m is equal to 1, then the characteristic Mach number is also 1. If m tends to infinity, then the characteristic Mach number becomes finite, is equal to gamma plus 1 by gamma minus 1. For air, it is approximately about 2.5. Okay, so that is what Prandtl proposed. Okay. And the relationship is m star square is equal to m square into gamma plus 1, 2 plus m square into gamma 1 minus 1. So this is the characteristic relationship between the characteristic Mach number and the local Mach number. So this is what we see here from the Prandtl's hypothesis. This is the relationship graph between. So here you can see the local Mach number on the x-axis. You can go up to whatever value you can go here, but then you see it is limited here, which is due to square root of gamma plus 1 by gamma minus 1. If in this case gamma is equal to 1.4, that is the situation here. So this is called the characteristic Mach number. Now let's look at how the properties do change. So initially, this is the situation here. What you see here, 1 is at this particular point here, 1, and this is the point 2. Here is the pressure, temperature, and when the shock occurs, you can see that the static pressure jumps spontaneously from here to here. The static pressure increases. So ideally, if you look at it, this one, this is the pressure P1 and this is the pressure P2. So here you can see that the pressure has increased all the way up here. And this is a temperature also has increased due to the formation of the shock wave. Now, for this static pressure, this is the corresponding stagnation pressure, which we looked in the last class. For this static pressure, this is the corresponding stagnation pressure. So now what we can see is due to the shock, the static pressure increases, but the total pressure, you can see that it is decreasing. Okay, so total pressure decreases. The rest of the properties increase and the Mach number decreases. So this is what you see here. The total temperature remains constant. The total energy remains constant. So when I say here, so this is the HT1 and HT2, they are equal. HT1 is equal to HT2. Total energy remains constant. Across the shock, the entropy increases. The total pressure, stagnation pressure decreases. The temperature, static temperature increases. The flow velocity decreases, which means the Mach number decreases. The flow is decelerating across the shock. All the static density increases and the pressure and the Mach number decreases. So if we have to analyze problem on normal shock, then probably, or in other words, if you wanted to really determine how the properties do change, so if we are interested in knowing what is the change in pressure, P2 by P1, T2 by T1, and how the properties change, that is what we are interested at the moment, how the properties change. So to do that, we have to go with the basic governing equations: the mass continuity equation, energy equation, and the momentum equation. What we have looked at, P1 plus rho 1 V1 square is equal to P2 plus rho 2 V2 square, and second law of thermodynamics. So we are basically interested in knowing how the properties change, all properties change across the shock wave. Now we are not going into the details of the derivation of how the properties change. If you want, we can do it, but we will not be effectively utilizing our time. But algebraically, we can manipulate these equations to determine how the property variation relations can be derived. There is no need for us to, at least in this course, there's no need to memorize anything. There's no need to remember any of these equations, because these are all summarized in the table which I have photocopied here. Now, the important thing for us is to know how to use this table here, which is in it's a randomly page, there's a number, page number is given, so it is page 21. This table is also called the NACA table, National Advisory Committee on Aeronautics. So there are two tables here. One is the table, first one is subsonic flow. The first table is just an isentropic relationships. Okay, so what all things we discussed here, let me so you can see that table 1 is the subsonic flow where there are no shock waves. So this is basically the relationship what we discussed, Pt by P is equal to 1 plus gamma minus 1 by 2 m square power gamma by gamma minus 1. So again, this T by Tt, it's written in inverse form, is equal to 1 plus gamma minus 1 by 2 m square. So all of these parameters are tabulated for a given Mach number. So no shocks are being formed until m equal to 1. It's a critical, as a hypothetical condition, m equal to 1. Critical condition. So that is the first table. The second table, what you see is the shock table. In the first part of it, you see this isentropic relationships at that particular Mach number, and the later part you can see here, if the Mach number, for example, let's say Mach number is 1.4, after the shock it will be 0.7397. So, and how the properties change across the shock is given through this expression, relationships here. Okay, so we will be trying to use this table and try and work out a problem. I think the problem is given in the problem sheet. A normal shock forms on the intake of an aircraft flying at Mach 1.6 at an altitude of 10 km from the ground. The corresponding static pressure and temperatures are given as 26.5 kilopascal and 223.3 Kelvin. Assume that the air has a specific ratio of gamma equal to 1.4. We are asked to find out what is the so here is the normal shock. So M1 is given, it is given flying at 1.6. We are asked to find out what is Mach number M2, what is total pressure PT2 after the shock, what is the static pressure P2 after the shock, what's the total temperature after the shock, and the static temperature after the shock. We also have this information. Prior to shock, the static pressure is 26.5 kilopascal. The static temperature T1 is 223.3 Kelvin. So just use the tables and so you have to go to M1 as 1.6 in the table, which is found on page 22. So for M1 equal to 1.6, then you should be able to find out what is the value of P2 by P1 from the table. What is T2 by T1 from the table? P2 by P1 is
2.820.
820. Okay. And what is T2 by T1?
1.358.
358 or 388? It's a bit difficult to read it, yeah. 388. I think it is 388. So you have to look at the number before and after. So that is, this is the one. Okay. And then you can find the value PT2 by PT1. PT2 by PT1 is
805.
0.80 or 8. I think it's 9.
8952.
8952. Yeah. So look at the number before and after to just check, because the printing is not very clear. It's copies after copies made and so on. Now, once you know these parameters, then you should be able to calculate what is the pressure PT2, the P2, TT2 and M2. Directly you can read what is the Mach number after the shock. It has to be subsonic value. What is the value? 0.6684. So now we have calculated one of the parameters here. So you can calculate from this, you can find P2, because P1 is already given. P1 is already given in the problem. P2 is equal to 74.73 kilopascal, and from this T2 is equal to 310 Kelvin. Now we have only static pressure upstream of the shock, so we can find PT1 by P1 is equal to 1 plus gamma minus 1 by 2 m square power gamma by gamma minus 1. From this we can find PT1, and once you know this value of PT1, we can find PT2. What's the value for PT1? 112.6 112.62 kilopascal. So from this you can find PT2. Yeah, you can find directly from the tables PT1 by P1 or P1 by PT1 could be given, I think. Yes. Yeah. So what is the value?
0.2628.
0.2628. 0.2358. So yeah, from this you can also calculate. Yeah. Right. Okay. Okay, so I got the value for PT2? Yeah. What's the value?
102.38.
102.38.
38.
Okay. It's similar values you get here.
100.8.
PT2 equal to 100.
100.8. Okay. Yeah. Okay. So this is just a starter for us to see how we can use this table. So the tables what we have here is the table which is valid for normal shock applications. Okay. So this is the situation when you have a flow encountering a normal shock, and this is normal shock. So when a flow encounters a normal shock, it just passes through, and here this is 90 degrees. The shock is normal to the flow. For this table is valid only for the normal shock. Okay. Now let's continue to look into this, like what we have seen from this normal shock. When we look at the supersonic flows, you can see that the signals which are communicating and they are overlapping on each other. So you can see that this is the very weak, it's not even a shock wave, but it is called the Mach wave. The signals are overlapping. So this Mach wave is the tangent of all the signals what we see here at this point here. Now the sound waves arising behind the source superimpose with each other to form in space a conic surface of high pressures. Now this is the schematic what you see here in this part here. So this is 90 degrees and this angle is mu Mach wave angle. The sign of this Mach wave angle is sin mu is opposite side AT by VT. At a particular time, this is this A is equivalent to the speed of sound what we are considering here, the velocity here. So now mu is equal to sine inverse of 1 by m. M is the Mach wave at which the flow is traveling. The Mach wave is the weakest of all kinds of waves. What we see here, it is not a shock wave. We can treat it as an isentropic solution. Now with this understanding, let's now move on. So here you see at subsonic speeds, there is no shock that is being formed. At low supersonic speeds, you start the initiation of the shock. Could be like that of a normal or a Bose shock. And as you increase the speed, the shock tends to hold on to the spike or the leading edge of the object at which. So this is the shock wave and then this is the spike of it. Now the strength of the shock wave is defined through its angle, to the angle. Now you can see that strength varies with higher speed. Now this is a complex phenomena what you see here because at higher speeds, so this is the Mach cone what we saw here. You have this oblique shock that becomes weaker as it moves further and eventually it becomes a Mach cone here. So when we have a shock that is normal to the flow, it's called normal shock. Not always you have this as a normal shock. At times, at different Mach numbers, this shock waves can also be inclined to this one. So now let's try and understand the theory of this oblique shock here. So now we have seen that this is the Mach wave, the flow that encounters the Mach wave will pass through. The flow will not turn, the flow will just pass through. And the other extreme, what we have seen is a strong shock wave, is a normal shock where the flow is orthogonal to this one, to the shock. The flow just passes through. So here is the weakest one, here is the strongest one. So anything that is in between, which is what we call as a beta, is the shock wave, is the oblique shock wave. Oblique shock wave. Now let's look at a situation of an oblique shock and a flow encountering the oblique shock with a velocity v1. Now this makes an angle beta. Beta is the oblique shock wave angle. The flow that passes through the oblique shock will not just go straight as we have seen for the Mach wave or the normal shock. Instead, the flow will turn by an angle theta, and theta is called the flow turning angle. So when we have a normal shock, the flow passes through the normal shock. When we have an oblique shock, the flow will not pass through in the same direction. The flow will pass through, but it will be inclined at an angle. Now, because it is inclined, the flow, even the flow that encounters the oblique shock is at an angle. It could be resolved into two components. One is the normal component, other one is the tangential component. So if I can say V1 will have a normal component, V1n will be V1 sine beta. Let me call this as 1 here. So here is the normal component B1n. And here we have this tangential component. Now similarly, the flow that is leaving also will have its components. Okay, so first let's look at the flow approaching the oblique shock. So now V1 n is equal to V1 sine beta, which is normal component, and V1 t is equal to V1 cos beta. Let me call this as equation 2. Now when I talk about V, obviously we shouldn't forget that there is also M1 there. There is a Mach number, corresponding Mach number. This M1 will also have a normal component M1n and M1t. It will also have a tangential component. So M1n is equal to M1 sine beta, M1t is equal to M1 cos beta. So this is from the from the intake side, the flow encountering the oblique shock. Now the flow that leaves the oblique shock, now this is the oblique shock, this is the flow that comes in here, which will have its normal component and the tangential component, which goes like that. But the flow that leaves the oblique shock will not go straight exactly, but it will be bent. Now, this also has its own component. It has its normal component as well as its tangential component. So here is this is V2, here it is V2En, and here it is V2 tangential component. It doesn't matter whether you use capital or small letters here. Now, when we are trying to work out the components, we are more concerned about the flow which has turned relative to the shock wave. So when we look at it, the flow has turned by an angle theta, but with respect to the shock wave, it has turned by an angle here, which is beta minus theta from the geometry. So then we can write here V2n is equal to V2 sine beta minus theta, V2t is equal to V2 cos beta minus theta. So this is equation 3 and equation 4. So if I now write here 1 divided by 2, I will get V1n by V1t is equal to sine beta by cos beta is equal to tan beta. Let me call this as equation 5. So similarly, if I divide 3 divided by 4, I can write here V2n by V2t is equal to tan beta minus theta. So now if I'm going to divide equation 5 divided by equation 6, I will get V1n by V1t on the left hand side. Then I have the whole thing divided by this V2n by V2t. So I'm just dividing equation 5 divided by equation 6. So this will be on the right hand side tan beta by tan beta minus theta, and this is equation 7. Is that clear? So let's leave this equation here at the moment, and then we'll come back to this bit later on. Now let's try and understand the governing equations for this oblique shock problem. So here is an oblique shock. Here is the flow that encounters the oblique shock with the velocity v1, and then this is the velocity v2. This is the problem what we see here. So the governing equations are the continuity equation, a momentum equation, energy equation, and the second law of thermodynamics. So if you look at the continuity equation, you can say rho 1 A1 V1 is equal to rho 2 A2 V2. But this is a continuity equation. But we know that when we are dealing with a continuity equation, we always look at the area that is normal to the flow. But in this case, the area of the oblique shock, this is at an inclination. So this continuity equation needs to be addressed to account for this one. So we need to resolve this area to be normal to this one here. So in other words, I should look at this as A1. So this is making an angle beta to the flow. So A1 will be A oblique shock sine beta. I'm resolving it. So it is like this. This is at an angle beta. So I'm now resolving it normal to it. So here I have rho 1 A of the oblique shock sine beta V1. Now again, if you look at the flow that is leaving this oblique shock, now this is if the pen is the oblique shock, my hand is this flow direction. Now we can see that this oblique shock area must be resolved to be normal to it. Okay, so which means we are looking at this is the angle beta minus theta. We want this to be the area A2. So if this hand is the oblique shock, this is the flow. If it is to be, this is beta minus theta. This is the cos of the included angle. It is tangential 1. And here is a sine of the included angle. Then it is normal to this one. So here A2 is A of the oblique shock sine beta minus theta. Understood, all of you? So that will be rho 2 AOS sine beta minus theta into V2. So this is the continuity equation here. So now we can see that there is common AOS on either side. The equation now reduces to the form rho 1 V1 sine beta. What is V1 sine beta 1? Sine beta, which is the normal component to the flow, V1n. So V1n. Is it clear? And similarly, I can write here rho 2 is into V2n, which is the normal component to the V2n. So the continuity equation reduces to the form rho 1 V1n is equal to rho 2 V2n. Now let's look at the momentum equation. Now, because the flow is at an inclination, you have again two components. One you have a normal component which is perpendicular to this oblique shock. The other one is the tangential component. The tangential component goes parallel to the flow. There is no pressure forces acting on it. So the momentum again has two components. One is the normal component momentum. Other one is the tangential component momentum. Okay. So the normal component is P1 plus rho 1 V1 n square is equal to P2 plus rho 2 V2 n square. That is a normal component. This is the one which is V1n, and this is the V2n. But then there is also a tangential component, which is going parallel V1t and then V2t, which is nothing but the tangential component with the mass flow rate rho 1 V1n. That is what we see here from the continuity equation here. This is the mass flow rate before, mass flow rate after. So mass flow rate into the velocity v1t, tangential component before, and that should be equal to the mass flow rate after rho 2 v2n v2n into v2t. Now again, if you look at this equation and if you look at the continuity equation, since rho 1 v1n is equal to rho 2 v2n, you can see that these two terms will cancel off in the tangential momentum. This results in the information to us that when you have an oblique shock and the flow that is going parallel to the oblique shock have the same magnitude, both before and after. So it is V1t is equal to V2t. So what does it mean? It means that this distance and this are same. That's what we see here. Okay, now let's look at the energy equation. Which is h1 plus half v1 square is equal to h2 plus half v2 square. So when we look at an oblique shock, here is the flow that is encountering the oblique shock with the velocity v1. The flow will pass through, but it will be inclined and move with the velocity v2, and the flow will turn by an angle theta. This flow that encounters the oblique shock at an angle beta will have its normal component v1n, and it will also have its tangential component v1t. Similarly, the flow that leaves the oblique shock at an angle beta minus theta to the oblique shock will have its normal component, which is v2n, and then it is v2t. Now you can apply the Pythagoras theorem. When you apply the Pythagoras theorem, you can say that v1 square is equal to v1n square plus v1t square. In similar way, we can write here v2 square is equal to v2n square plus v2t square. So the energy equation becomes h1 plus half v1n square plus half v1t square is equal to h2 plus half v1 V2n square plus half V2t square. From what we have deduced before, V1t is equal to V2t. Now, applying this condition to the energy equation, we can say that V1, the kinetic energy contribution coming from the tangential, are same on either sides. They cancel off. Then the final energy equation reduces to the form H1 plus half V1n square is equal to H2 plus half V2n square. Okay, and then the second law of thermodynamics. Thermodynamics must be satisfied, which is S2 should be greater than S1 across the oblique shock. Now, let me summarize the equations what I have deduced so far for an oblique shock. When you have an oblique shock, when you have a flow encountering an oblique shock at an angle beta, which is basically the shock wave angle, the flow will pass through, but it will not go in the same line. The flow will turn. The flow will turn by an angle theta, and it will move the velocity v2, which will be reduced velocity. The flow will be decelerated. The flow itself will be at an inclination of beta minus theta to the oblique shock wave. Okay, this flow encountering oblique shock at an angle, it will have its normal component v1n, and also we have this normal component at the exit v2n. Okay, we also will have this tangential component, and then we also will have this tangential component v2t. So the governing equations are, the continuity equation is rho 1 v1n is equal to rho 2 v2n, and the momentum equation is p1 plus rho 1 v1n is equal to p2 plus rho 2 v2n square. And then the energy equation h1 plus half v1n square is equal to h2 plus half v2n square, and S2 is greater than S1. Now, if we look at this governing equations, these are the governing equations which we deduced for an oblique shock. Now, let's recollect what we did for the normal shock. When we have a normal shock, here it is the flow that encounters an oblique shock, which is normal to it. Here it is V1 and V2, flow will not bend, and here it is rho 1 P1 and H1. So here it is H2, rho 2 and P2. So the equations, governing equations are rho 1 V1 is equal to rho 2 V2, and here momentum P1 plus rho 1 V1 square is equal to P2 plus rho 2 V2 square. H1 plus half V1 square is equal to H2 plus half V2 square, and S2 is greater than S1. So this is the case for normal shock. And the table what we have had, what we discussed, is for the normal shock tables. Normal shock tables. What you have is a normal shock table. This is not an oblique shock table. So we cannot use this directly for an oblique shock problem. But from the analysis done, what we have done, it clearly shows that when we have an oblique shock, if we can resolve the flow normal to it, V1n, and then V2n. Now you can see, look at the governing equations here. They are now reflecting the normal shock phenomena here. So this normal shock wave tables could be used for oblique shock problems by resolving the flow normal to the oblique shock so that it becomes normal shock problem. That's how we have to use it. That's what we see here. Okay. Now, with this understanding, now let's go back to this equation, what we have obtained and what we have left. So we have V1n by V1t into V2n by V2t is equal to tan beta by tan beta minus theta. This was equation 7. Now, from this analysis, what we have done, we were able to infer that V1t is equal to V2t, and because of this, we didn't know at that time. Now we can say these two terms cancel off. So this becomes V1n by V2n is equal to tan beta by tan beta minus theta. This is equation 8. Now if I multiply and divide this equation with C star and with C star, what do I get? I will get M1 n star divided by M2 n star. Is that clear? Understood? Multiplying and dividing it by C star. This is equal to tan beta by tan beta minus theta. Now applying the Prandtl hypothesis, I can write here, this is M1 n star square, because M1 n star into M2 n star is equal to 1 by M1 n star. This is from the Prandtl hypothesis. So this equation becomes M1 n star square, which is equal to tan beta by tan beta minus theta. And we have seen that there is a relationship between the characteristic Mach number and the local Mach number, gamma plus 1 divided by 2 plus m square into gamma minus 1. At the beginning itself, we saw this one. There is a relationship. We didn't derive this, but going into it will take time, but this is the relationship. So accordingly, I can write here M1 n star square is equal to M1 n square into gamma plus 1 divided by 2 plus M1 n square into gamma minus 1. Understood? So now we can write here this. Okay, now let me write this equation as M1n is M1 sine beta. We got this from the very beginning here. Here you see this one here. M1n is equal to M1 sine beta. M1t is equal to M1 cos beta. So similarly, here also there is M2. Here M2n is equal to M2 sine beta minus theta, and M2t is equal to M2 cos beta minus theta. The same argument like what we used for V2 velocities here. So this equation will be m1n m1 square sine square beta into gamma plus 1 divided by 2 plus m1 square sine square beta into gamma minus 1. So if I can write this equation in general terms, I can write here I was just trying to expand what m1 square is. That's exactly what I have done here, m1n square here. But we are dealing with an equation. This is the equation we are dealing with here. Okay, so I can write here tan beta by tan beta minus theta is equal to m square sine square beta into gamma plus 1 divided by 2 plus m square sine square beta into gamma minus 1. And this relationship is called m beta theta relation. So if we know two parameters, then we can calculate the third parameter, and this is very helpful information when we are solving an oblique shock problem here. So when a flow encounters an oblique shock at an angle beta, the flow encountering with the Mach beta, now what you see here, the flow turns by an angle theta. Is that clear? So this is the information what we have, m beta theta we have. Now let's try and plot this relationship on a graph, and then we'll try and take it forward from here. So let me on the x-axis, I'm using theta as the flow turning angle. On the y-axis, I'm using beta, which is the oblique shock wave angle. Now we are having this equation in mind at the moment. This is the equation which we have in mind. Now we have looked at the two situations at the start. One for a Mach wave, the flow will not turn. The flow will pass through. Mach wave, mu is equal to sine inverse of 1 by m. That's what we saw. And the next extreme cases is a normal shock where the flow is orthogonal pi by 290. The flow will not turn. So under these two extreme cases, what we have here, the flow turning angle theta is equal to 0. Okay. Now apply that condition here. We see at this point here where theta equal to 0, there are two solutions possible. One, it could be either a normal shock wave or it could be a Mach wave, mu. So if I choose a particular Mach number, choose m, for a given Mach number, if I vary theta for a fixed value of m, varying theta and beta, I will get a graph, something like this. Get a graph like that. This is from this equation. If you use your write a small program, fix the value of m, vary the beta and theta for a given value of gamma, this is the graph what you'll get. So this is for a given value of m. Now if I vary the m, if I reduce the value of m, then my graph will be something like this. If I reduce the Mach number further, then it is, the shape will be preserved. Reduce the Mach number further, reduce the Mach number further, I'll get something like that. Now, a couple of observations what we are going to make at this particular point. For a given Mach number, let's say this is m1 for our understanding purpose. For a given Mach number for m1, you can see that there is one theta max, which means for a given Mach number, now this is the theta max. So what does it mean here? When you have a flow encountering and then you have a concave corner, so you have an oblique shock. If this is an angle theta, there is an oblique shock. There is an oblique shock. This will cause the flow to turn exactly by the angle theta. Now, you can have the flow turn up to theta max. Up to theta max, the shock will be up to theta max, the shock will hold on to the tip. And you have an oblique shock solution. But once the value theta is greater than theta max, then flow cannot hold on to it, then it becomes a bow shock. You don't have an oblique shock solution. Okay, so for a given Mach number m, there is one theta max value. Okay, the second thing what we are going to say here is for theta less than theta max. Okay, now before I proceed further, let me try and complete this what I said. So here for this is the okay, so it has to be one continuous smooth line here. So this is theta max. Now just below that, you will have this green line. What is it? Is m2 equal to 1, which is the sonic line. So m is supersonic, and along this line you have m2 having a critical value m2 equal to 1. This is the sonic line. Okay, now let's just proceed further now. For theta less than theta max, so what we are saying here is that when we have an m beta theta relationship, so this is beta theta m, and this is theta max, which is only one theta max for one value of m. So for theta less than theta max, then there are two possible solutions, which means at any particular value here you take, there are two solutions here. One is the strong solution, other is the weak solution. The two solutions there. For theta less than theta max, there are two possible solutions. For a given value of theta less than theta max, either you can have a strong solution or a weak solution, which means for a given flow turning angle of theta, there is this beta. We don't know whether we are going to have the strong solution always, but from the research and from the established literature, we will always have the weak solution. Okay, so we'll always have the weak solution. So that is what we see here. So for example, if for a given value of theta less than theta max, then you can see that there is, for that value of m1, so you have this value here, beta 1. This is the weak solution. And then if we move further here, then this is the strong solution. We don't know whether it exists or not, but always we know for sure the weak solution exists. Okay,